Okay, let's get started. So assignment 2 was due last night. I'll probably start grading it tonight or tomorrow. I posted most of assignment 4 just now. Assignment 3. I posted most of assignment 3 just now. 4/5 of it. I'll post the rest of it on the weekend. The 4/5 of it that I posted, you can already work on because that's all about completeness. I don't know yet what problem 5 will be about. For some reason, when I put it on Canvas, I called it assignment 4, and when I put it on Piazza, I called it assignment 2, but it's assignment 3. I fixed it after the fact. So what we finished talking about completeness last lecture, and then what we started doing, and I ran out of time to get before we really got anywhere, is what we want to do is prove a characterization of spaces of constant curvature. A space of constant curvature means a Riemannian manifold with sectional curvature equal to a constant. Okay, we're going to prove that if it's simply connected, let's say complete simply connected constant curvature, then it's isometric to one of the standard models that I showed you before, suitably scaled so that the constant is +1, -1, or 0. And before we can do that, we need a sort of more general result, which is the theorem of Cartan, which in some sense says that if you know the metric in some precise, if you know the curvature in some precise sense, then you know the metric. And the precise sense is what we were trying to get to on Monday, but we ran out of time. So I'm going to repeat the things we did in the last 20 minutes of Monday's lecture without the explanations for why those things are true, because we did that. And then I'll continue until I get to the theorem very quickly, and we'll prove that. So we'll prove that theorem. It's not going to be hard. With this theorem, the hardest thing about it is the notation, right? It's a trivial proof. And then we're going to use that to characterize the constant curvature spaces. So this was where we were. We said let M and M tilde be Riemannian of the same dimension, N. Let P be a point in M and P tilde be a point in M tilde, and choose an isometry, a linear isometry iota from TPM to TP tilde of M tilde. We explained last time that we can always do this. So this is an inner product space with metric GP, where G is the metric on M, and this is an inner product space with metric G tilde, P tilde, where G tilde is the metric on M tilde. And let's let V be a normal neighborhood of P in M, such that the exponential map on P tilde, the exponential map of P tilde is defined on I of exp P inverse of V. So let me draw a picture. This is M. This is M tilde, P tilde. I got brand new chalk today, which is good because they're not microscopic, but they're harder to hold at the same time. So there's some neighborhood V here, which is the image under XP of some open neighborhood of the origin. This should be star shaped. It doesn't look like it, but TPM. And then I is the linear isometry onto T, P tilde, M tilde. And this is mapping us onto some I of XP inverse of V. And so we've chosen V, we've chosen this normal neighborhood of P, so that when I take, this is diffeomorphic to a star-shaped neighborhood of the origin in TPM. When I map this over by I, this is contained within the domain of X of P tilde. So I can apply X P tilde to anything in here. And we saw that we can do that. And then we defined a map, define F from V into M tilde by F of Q is exactly what you would guess, right? I take a point here. Let me use another color. I take a point Q in here, and I follow it back from here to here, and then to here. This is f of Q. And you can see that f of P is P tilde, because x of P takes the origin to P. So x P inverse will take T to the origin. This is a linear map. It takes the origin to the origin, and this has to take the origin to P tilde. Okay, and this is obviously smooth, because it's the composition of smooth maps. Then the next thing we did was we said, let fix a point Q in V. There exists a unique normalized geodesic gamma from 0t to m to m. So that means that the distance from P to Q is t. So we know that this is true because V is a normal neighborhood. So there's a geodesic here, gamma. And then we said, let gamma tilde be the normalized geodesic in M tilde with gamma tilde of 0 is P tilde, and gamma tilde prime at 0 is I of gamma prime of 0. Okay, so we have some initial velocity for this geodesic here, and we're going to find a geodesic gamma tilde. I'm going to show you that it goes through f of Q in a second, with initial velocity I of gamma prime of 0. So gamma prime of 0 is a unit vector because gamma was a normalized geodesic, and I is an isometry, so this is a unit vector. So this is a normalized geodesic. And we know, in fact, gamma tilde of T is x P tilde of I T gamma prime of 0. Right? If you want to find the geodesic with initial velocity, this guy, and we want to follow it for time t, we take that initial velocity multiplied by t and apply the exponential map. So if we rearrange this, this becomes x p tilde composed x p inverse of x p of t of gamma prime of 0. But this is just gamma of t. And this is just f. So hence, gamma tilde of t is f of gamma of t. I should call this, sorry, this is going up to time t. So let me call this s. S. And this is for all s in 0t. Okay, in particular, gamma tilde of t is f of gamma of t, which is f of p, which is p tilde, right? Because this geodesic, sorry, there exists a unique normalized geodesic I didn't write down joining P to Q. This means that gamma of 0 is P and gamma of T is Q. Okay, so I think I got to here on Monday. I didn't do this calculation, right, which I just did. So this geodesic gamma tilde is just the image under F of gamma because of the way we defined F. So this yellow geodesic here gets mapped by F. Gamma tilde of T is F of gamma of T. Gamma tilde of S is F of gamma of S for all S in 0t. Okay. So now we're almost ready to state the theorem. Let PT be parallel transport along gamma from P, which is gamma of 0, to Q, which is gamma of t, and let PT tilde be parallel transport along gamma tilde from P tilde, which is gamma tilde of 0, to gamma tilde of t, which is f of P tilde. Which is, sorry, which is f of, what have I done here? This is f of Q, which we can call Q tilde. This is the definition of Q tilde. To gamma of t, which is f of Q. Okay. And now we know that I is an isometry, iota is an isometry, and we know that parallel transport is an isometry. So if I define phi t from TQM to T f of Q m tilde by phi t of V is PT tilde compose I compose PT inverse of V for V in TQM, then this phi t is a linear isometry. Parallel transport is linear and it's an isometry, and iota is also a linear isometry. So this is a composition of linear isometries. Let me draw another picture. A little bit bigger. So there's M tilde. We have P and Q. Let me draw it bigger. This is all in the same normal neighborhood. We have gamma, and on this side we have P tilde and Q tilde, which is f of Q, and this is f of P. And then we have gamma tilde, which is f of gamma. And what we've done is we've said from this tangent space to this tangent space, we have a linear isometry, which is given by, you take a vector in this tangent space, you parallel transport it back. So this is step 1, 2. You transport it back to P using the parallel transport along gamma inverse. Then you map it to here using I, and then you parallel transport it. Step 4, you parallel transport it over there along gamma tilde. Okay, so there's a linear isometry from TQM to TQ tilde M tilde. Okay, now we can state the theorem. Yep. With it, you're right. I called it tilde, yeah. Okay, so, and let's let R and R tilde be the Riemann curvature tensors of M and M tilde respectively. Okay, so this is the theorem with all of that notation out of the way. Suppose that for all Q in V and all X, Y, U, V in TQM, that we have that the inner product of R of X, Y, U, V is equal to the inner product R tilde of phi tx, phi ty applied to phi tu and then phi tv. And of course, this here is the metric G on M. And this is the metric G tilde on M tilde. This is the only thing that makes sense. Then this map F, this smooth map F that we defined, is a local isometry. And the push forward at P, which goes from TPM to T F of P, which is P tilde of M tilde, equals I, iota. Okay. So if along, if for every point Q in this normal neighborhood V, I can do this construction. I get this linear isometry phi t. There's a linear isometry from this blue tangent space to this blue tangent space. If the curvature tensors agree at every point Q and V with the curvature tensor at Q tilde in M tilde using in this sense, then this map is a local isometry and its push forward at P is the iota that I started. Okay, so somehow it says that if you know what the curvatures are, then you know what the metric is up to isometry. Okay, so let's prove this. I shouldn't have erased the definition of F, so let me rewrite it. Remember, F was X P tilde composed iota composed XP inverse, XP inverse. So it's immediately, so here's the proof. This guy is smooth, so it definitely has a push forward. We can automatically see that this push forward is iota because the push forward of composition equals composition of push forwards. That's the chain rule. And XP star at the origin is the identity. And the same for P star, for P tilde. Right? We know that the push forward of the exponential map at the origin is the identity. So if I push forward this at P, P takes this guy to the origin, and this takes the origin to the origin. So if I do that, I get F star P is equal to XP star at 0 inverse. And it's also true that the inverse of the push forward is the push forward of the inverse. Tilde star 0, right? So that's the identity. And I also use the fact that the push forward of a linear map is itself. The derivative of a linear map is itself. So that's the identity, that's I, that's this, so that's I. So this last part is trivial. We just need to see why F is a local isometry. So we need to show that the push forward is injective at every point. And not just injective, is an isometry. So to show F is a local isometry, we need to show that F star Q, which goes from TQM to T F of Q M tilde, is an isometry. Because, I'm not going to write all these words, if it's an isometry, it's invertible, right? So if the push forward is invertible at every point, then of course it's a local diffeomorphism. And then if it's a local diffeomorphism, what does it mean to be a local isometry? It just means that the push forward is an isometry at every point. Okay, so that's what we have to do. Okay, so So for Q and V, we know that gamma, there exists a unique normalized gamma from 0L to M, such that gamma of 0 equals P, gamma of L equals Q. I was calling this T before because I wanted to do this for all T at the same time. It's 5T, right? But now I'm going to do it for a fixed point Q, which has some distance L. Let's let V be in TQM. We need to show that F star Q applied to V has the same norm as V. So this is the norm in T Q tilde M tilde. And this is the norm in TQM. If we can show this equation, we'll be done. Okay, and we're going to do it by using Jacobi fields. So let J be a Jacobi field along gamma with J of 0 equals 0 and J of L equals V. So as an aside, how do I know this exists? When we looked at properties of Jacobi fields, you know, initially we know it's a second order linear ODE. So if we prescribed J and J prime at time 0, it exists and is unique. But when we did the properties of Jacobi fields, we saw that instead you can prescribe the boundary conditions, the initial value and the final value, and it'll exist and it'll be unique, provided there are no conjugate points along gamma. So an aside, this exists and is unique by the previous result, because XP is a diffeomorphism on V. It's a normal ball onto V on XP inverse of V, right? That's how we define V. It was a normal neighborhood. So XP has no critical points in this set. So P equals gamma of 0 has no conjugate points to it along gamma along gamma, and hence there exists a unique Jacobi field along gamma with prescribed boundary data, prescribed boundary values. So at this point in the book, Do Carmo just says, let J be a Jacobi field with this, right? And he doesn't remind you why you can do this, because you can't always do that on any geodesic. It's because we're staying inside the domain of a normal neighborhood. Okay. So now let E1, E2 up to En minus 1, and then En, which is gamma prime at 0, be an orthonormal basis of TPM, any orthonormal basis of TPM, and where the last one is the initial velocity of gamma. And I can do that because gamma is a normalized geodesic. That's a unit vector. And let E1 of T, E2 of T, En minus 1 of T, and En of T be the parallel transports of E1 up to En along gamma from P, which is gamma of 0, to gamma of T. Okay. Then we know that E1 of T up to En of T is an orthonormal basis of T gamma T M. And this is for all T in 0L, right? Because parallel transports on isometry. So we can write J of T is the sum from K equals 1 up to N of some function yk of t, ek of t. So yk goes from 0L to R, and it's smooth. Jacobi fields are smooth. Okay, and this satisfies the Jacobi equation. By the Jacobi equation, we know that J double prime plus R of J gamma prime equals 0. So if I plug in what this is, the first thing to recall is that because these were chosen to be parallel, J double prime is the sum over K of YK double prime EK. I'm dropping all the of T's here, right? Because EK is parallel. And then if I plug that in there, I get the sum over K, YK double prime EK plus R of the sum over L, YL, EL, and then En prime, En applied to En equals 0. What have I done? Oh, sorry, I didn't. No, that's right. That's right. Gamma prime. That's right. So let's take inner product with, let's say, EJ. And because they're orthonormal, the E1 up to En are orthonormal for all T. If I take the inner product with En here, I'm just going to get a Y with EJ. I'm going to get a YJ double prime plus the sum over L R of EL, En, En. What have I done? What have I done? 2, 3. That's right. En, EJ, and then YL equals 0. I changed the subscripts from what I have in my notes, and I'm probably going to come to regret that later. But anyway, so there's a sum over L here. There's a J. N is fixed. Okay. So this is the equation. This is the system of ODEs that are satisfied by the Y's. Now, let gamma tilde be as before. As before. So we know the gamma tilde of 0 is P tilde. And in fact, gamma tilde prime of 0 is I, gamma prime of 0. And we showed that gamma tilde is F composed gamma. This is all these facts that we know. Define a vector field J tilde along gamma tilde by J tilde of T is phi T of J of T. Okay, so for T in 0L. Remember that phi T was, it goes from gamma of T to gamma tilde of T, the tangent space to M at gamma of T to the tangent space to M tilde at gamma tilde of T, and it's a linear isometry. Okay. So, and let's also define EK tilde of T to be phi T of EK of T. So hence, J tilde of T is the sum from K equals 1 up to N of YK of T times EK tilde of T. Because the definition of J was this, And J tilde was phi t applied to this, and phi t is linear. So the y's come out, and we just get these ek tildes. Also, by hypothesis, remember, I've erased the statement of the theorem a long time ago. The statement of the theorem says that R of EJ, EN, EN, let me keep the symbols the way I have them there. L, if I want to keep it consistent with the way I wrote it in the theorem, let me write it like this. It's the same thing, right? It's just another way of writing the Riemann curvature tensor. So R of EL, EN applied to EN, inner product EJ, this is the same as R tilde of EL tilde, EN tilde. Oh, not yet. Oh, this is right. En tilde, EJ tilde for all t in 0L. Right? Because I've defined these guys to be the phi t's of them. So the hypothesis was exactly that if you evaluate the curvature on 4 vectors at Q, then that's equal to the curvature R tilde on the images under phi t of those vectors. Okay, this is exactly the hypothesis. And now you can see what we want to do. We want to show that J tilde is a Jacobi field. But before we can do that, we need to prove that En tilde is the velocity of gamma tilde. So we also have gamma tilde prime of t is pt tilde of gamma tilde prime of 0. This is because this is a geodesic. So we know that the velocity vector field is parallel along itself. That's what it means to be a geodesic. So if I want to calculate the velocity at time t, I just take the velocity at time 0 and I parallel transport it. But that's equal to I gamma prime of 0, because gamma tilde prime of 0 was defined to be this. And then again, that's equal to pt inverse gamma prime of t. Again, because gamma is a geodesic. Okay, but that's equal to phi t of gamma prime of t. Okay, so hence En tilde of t is equal to phi t of En of t, which is phi t of gamma prime of t, and we just showed that that's equal to gamma tilde prime of t. Okay, so if I use this fact, this becomes equal to R tilde of EL tilde gamma tilde prime gamma tilde prime EJ tilde. Okay, so now let's use this hypothesis and the Jacobi equation the star becomes y double prime j plus the sum over L. I can now put these R tildes, EL tilde, gamma tilde prime, EJ tilde YL. And if I multiply both sides by EJ tilde and sum over J, I get J tilde double prime plus R tilde, J tilde, gamma tilde prime equals 0, right? Because if I sum this by EJ tilde and add, I get J tilde double prime. Again, these are parallel by construction. And this is exactly going to give me, the YL is going to come in here. The sum over that's J tilde. And then the EJ, this is the EJth component. So this is what I get. Okay, so hence J tilde is a Jacobi field along gamma tilde. Now you can, we're almost done. Now you can see essentially that the hypothesis we put in the statement of the theorem is exactly what we need to be able to ensure that when we start with a Jacobi field along gamma and do this define J tilde by phi t of JT, we want to make sure that that's a Jacobi field. So that's what we had to do. Okay. Almost done. So moreover, J tilde of 0 is phi t of J of 0. But J of 0 is 0, and this is linear. So J tilde of 0 is 0. Okay. And since phi t is an isometry for all t, we get that J tilde at time L is the same. Well, it's phi t, phi L, JL, which is equal to the norm of JL, which is equal to the norm of V. So you see that all that we have left to do now, so it remains to show that J tilde of L is F star P, sorry, of V. If we can show this, then we're done. All right. So how are we going to show this? Well, J tilde of T is phi T of J of T. And that's equal to PT tilde I PT inverse JT. So let's compute its initial velocity. Okay. So this thing depends on T in 3 ways. It depends on T here and here and here. So I'll have a product rule. So one term where I differentiate this guy, and differentiating the parallel transport gives you some kind of covariant derivative. You may have seen this before, but it doesn't matter because whatever I get when I differentiate this, it's a linear map in T. It's smoothly varying in T, and it's a linear map. I'm going to get some linear map, and then I'm going to apply it. I'm going to set T equal to 0. So I'm going to apply it to J of 0, and J of 0 is 0. So it doesn't matter what the derivative of this is with respect to T, because when I evaluate this whole thing at T equals 0, after I differentiate that, I'll get 0. Same thing with this guy. So I'm using the fact that J of 0 is 0. I'm going to just end up getting J prime of 0 here. But P of 0 is the identity. Parallel transport along the constant curve is the identity. And so is P tilde of 0. So this is just I J prime of 0. Okay, so I know what the initial value of this Jacobi field is and its initial covariant derivative. But we had a result earlier in the course which exactly gives us a formula for the Jacobi fields with initial value 0 given in terms of their initial covariant derivative. So J of T, J and J tilde are Jacobi fields with J of 0 equals 0 and J tilde of 0 equals 0. So by an earlier result from the course, we know that J of T is X P star at T gamma prime 0 applied to T J prime of 0. And the same thing for J tilde. J tilde of T is X P tilde star T gamma tilde prime of 0 T J prime of 0, J tilde prime of 0. Okay, but here I can use the fact that I know that gamma tilde prime of 0 is I gamma prime of 0. And I know that this one is I j prime of 0. Okay, so now we're done because of the following. So evaluate these at t, at t equals L. What happens if I evaluate these at t equals L? I get J of L is exp p star L gamma prime of 0 applied to L j prime of 0. So if I invert this, I get a typo in here. I've got a typo in my notes. So if I invert this, I get L j prime of 0 is equal to exp p star L gamma prime of 0 inverse applied to J of L. Okay, and now I'm going to plug this into there. J tilde of L is exp p tilde star at L I gamma prime of 0 compose I composed exp. So what am I doing? I'm trying to do in two steps. I'm putting in t equals L here, and then this I'm pulling out the iota, and then I'm writing L of j prime 0 in terms of this. Inverse J of L. Okay, but this is exactly saying, what is this guy? This is F star Q of J of L, right? Because this guy, XP of L gamma prime of 0 is Q, and XP tilde of L gamma tilde prime of 0 is F of Q. Okay, so when you translate what that says, this says exactly the push forward of F at Q. And that's what we wanted to show, right? We wanted to show, let's just finish one more line. So J tilde of L is F star Q of J of L, which is F star Q of V. And somewhere earlier I said that's what we needed to show, right there. Okay, so that's the end of the proof. It's a lot of steps and a lot of notation, but if you pay attention to what we've been doing, you have these two Riemannian manifolds of the same dimension, and you choose 2 points, and then you say choose a linear isometry from TPM to TP tilde of M tilde. And then you want to say for a sufficiently small normal neighborhood, if I follow geodesics there to a point Q, then I can do this construction where I get this map F by parallel, I define F, I define phi t, and then you say, what do I need? What condition do I need on the curvature to ensure that a Jacobi field on gamma gets mapped to a Jacobi field on gamma tilde by phi t? And that's exactly the condition we had to impose to be able to then conclude that we get a local isometry. So F from V to M tilde is a local isometry. Okay, so this is a local result. It has nothing to do with constant sectional curvature. We're coming to that in a few minutes. And so we didn't need completeness here because it's not a global result. It's a local result. Sorry, I need to drink water because I got too much chalk dust in my lungs. Okay. So in fact, we're only going to care about 2 immediate corollaries of this theorem. which are going to apply to the constant sectional curvature case. But before I do that, I want to state, give you an aside remark. Probably pedagogically, I should do the corollaries first and then do the remark. But since the statement of the theorem is long gone anyway, it doesn't matter. So here's an aside. One can ask a related global question. It's the following. Let mg and m tilde g tilde be Riemannian. And suppose f from m to m tilde is a diffeomorphism such that the pullback of the Riemann curvature tensor on m tilde is equal to the Riemann curvature tensor on m. Then is it true that f is an isometry? I.e. that f star of g tilde equals g. Okay, so certainly if this diffeomorphism was an isometry, this would be true. It would pull back the curvature on the target to the curvature on the domain. But the question is it an if and only if? In other words, if you know that two Riemannian manifolds are diffeomorphic, and this diffeomorphism takes the curvature of one to the curvature of the other, do they have to be isometric, right? And what this really means is, does the curvature uniquely determine the metric? So i.e., does curvature uniquely determine the metric? What we just proved was some kind of local version of this in a very precise sense of what we mean for the curvatures to agree, right? We constructed a very particular local diffeomorphism that turned out to be a local isometry. And the answer, yep. Yes. Yeah. Yeah, I'm not saying we're not using this to find what the metric is. We're just saying, could it be that there's, let's say you fix a manifold M and a fix a metric G, so it has a curvature, right? Let's say you have two different metrics on the same manifold, right? And we can say they both give you curvature tensors. There's no reason for those to be the same, right? But let's say there's a diffeomorphism that if you act on the function by the diffeomorphism, it takes the curvature of metric 1 to the curvature of metric 2. Does that mean you have to take the metric 1 to metric 2? In other words, is the only metric that gives you a given curvature that one, right? So G will give you a curvature R. The question is, can there be some other G which would give you the same R? Okay, and the answer, surprisingly, is subtle. Okay, so first of all, when n is 0 and n is 1, there's nothing to do. Everything is flat. If n is 2, the answer is no. So see the textbook. He gives an example without, putting in the details, draws a picture. You can have in dimension 2, two metrics which are not isometric, and yet their curvatures are basically the same. When n is at least 4, I'm going to put yes in quotation marks. This is a result of Kulkarni from the 60s, late 60s. It was his PhD thesis. But I put in quotation marks because some references I'm looking at say you might need the assumption that MG is real analytic, that they're both real analytic. You have to work in the real analytic category, because some discussions of this theorem that I've read say you need analytic, some don't. So I haven't actually looked at the original paper to see what is required. And when n equals 3, it's more subtle. And there's a paper by Yao from the early 70s where he discusses this question. And the references are all in the textbook, so you can look at these papers and have a look. But I had never even heard about this problem before I prepared this lecture, so I don't know much about the details of that. Okay. So let's state two corollaries, as I said, of this theorem, and then we'll be ready to classify complete simply connected constant sectional curvature. Okay, corollary one. Let M tilde be spaces of constant sectional curvature of the same dimension and the same constant sectional curvature. So I'm being sloppy here, right? I'm saying there's a Riemannian metric on here. They have the same dimension. There's a Riemannian metric on here. There's a Riemannian metric on here. And the sectional curvatures of these two metrics are both constant, and it's the same constant. Okay. Let P be a point in M and P tilde be a point in M tilde. Let E1 up to En be an orthonormal basis of TPM, and E1 tilde up to En tilde be an orthonormal basis of P tilde M tilde. Then there exists a neighborhood V of P in M and a neighborhood V tilde containing P tilde in M tilde, and an isometry F from V to V tilde such that the push forward at P of EK is EK tilde for all K. Okay, and this is immediate from the previous result. Let's let I of EK be EK tilde for all K. That determines I, and that's a linear isometry. In fact, that's how I showed you can always choose such a linear isometry. The condition that we need for the curvature tensors is automatic because both have the same constant sectional curvature. Right? So we know that if you have a Riemannian manifold with a constant sectional curvature, K, then you can write down what the Riemann curvature tensor is in terms of the metric exactly. And therefore, this condition becomes automatically satisfied. And so the lemma gives, so the theorem, the Cartan theorem, gives F from V to M tilde local isometry with F star P is I, and now shrink V such that F from V to F of V is a diffeomorphism. Right? What's a local isometry? It's a local diffeomorphism which induces an isometry at every point. Right? Since this is a local diffeomorphism, I can suitably shrink the domain. I know there's some possibly smaller open neighborhood of P contained in V. So let me just change V to that, on which it's a diffeomorphism onto its image. And it's a local isometry, therefore it's an isometry. It's an isometry. Okay. So it says that locally, any two spaces of the same dimension that have the same constant sectional curvature are isometric. This corollary says that locally any two Riemannian manifolds of the same dimension and same constant sectional curvature are isometric. Okay, what does that mean? I mean, if I have two Riemannian manifolds, the same dimension, the same constant sectional curvature, I take any 2 points in them, there'll be a neighborhood of the first point and a neighborhood of the second point, and an isometry between those two neighborhoods. You're talking about the symplectic geometry, Darboux theorem? It's a version. Yeah, I mean, there are other things you can say. So the Darboux theorem in symplectic geometry, if you know, it says any two symplectic manifolds are locally symplectomorphic, not globally. And it's not true that any two Riemannian manifolds are locally isometric. But if they're both constant sectional curvature, that's true. They're locally isometric. There's more you can say than just this, but not much more. Yeah. I mean, you see that from the Cartan theorem, essentially the curvature, you know, I could have this business about shrinking the domain at the end. I could have done that in the Cartan theorem. I said, by further shrinking V if necessary, we can assume V is an isometry onto its image, right? So it says that if you know that the curvatures agree in the sense of that theorem, then locally those manifolds are isometric. Okay, corollary 2. Let M be a space of constant curvature, constant sectional curvature. Just a single Riemannian manifold. And let P and Q be 2 points in M. Let E1 up to En be an orthonormal basis of TPM. Let F1 up to Fn be an orthonormal basis of TQM. Then there exists a neighborhood U containing P and a neighborhood V containing Q and an isometry H from U to V such that H star of EK, H star P of EK is FK for all K. And proof, take M tilde equals M, P tilde equals Q in corollary 1. Okay, there was no reason in corollary 1 why those have to be different Riemannian manifolds. If I take the same Riemannian manifold, I guess G tilde equals G, right? If I take a single Riemannian manifold with constant sectional curvature and I apply corollary 1, it says that in a Riemannian manifold of constant sectional curvature, any 2 points have neighborhoods which are isometric to each other. Okay, and not just isometric, I can even choose that isometry to take any orthonormal basis to any other orthonormal basis. Right? I can prescribe the orthonormal basis. I can prescribe the push forward at the identity. So, i.e., for any constant sectional curvature space, any 2 points have neighborhoods which are isometric, not just isometric, but with a prescribed push forward at those points. Any 2 points have neighborhoods which are isometric where, so UV, isometric where H from U, it goes from U to V is the isometry, H takes P to Q, and H star of P from TPM to TQM is prescribed, can be prescribed. Okay. So this is saying that the neighborhoods are the same in a very strong sense, right? I can even prescribe the push forward of the isometry to be whatever I want. Okay. I have 20 minutes. There's no way I can finish. Maybe I want to state the next theorem, which I've been hinting at before, and then we'll start working on the proof, but we'll need a little bit of next Monday. So we're going to apply these corollaries. We'll apply these corollaries to the following. This is the main theorem of chapter 8. So let Mn G be complete. This is another global result. Complete with constant sectional curvature little k, which is either -1, 0, or +1. Right? We already showed last class that by scaling by a positive constant, we can ensure this is true. Okay. Then, if M is simply connected, then M is isometric to hyperbolic space with the hyperbolic metric if k is -1, Euclidean space with the Euclidean metric if k is 0, and the round sphere with the round metric if k is +1. So of course here I want n at least 2, right? Because if n equals 1, everything is flat. Everything is just uninteresting. Okay, and of course these are all we've talked about already. We know from the Cartan-Hadamard theorem that Hn is diffeomorphic to Rn as a manifold. Right? So they have the same underlying manifold up to diffeomorphism, but these are different metrics because this has constant sectional curvature -1 and this is flat. And this one is simply connected when n is at least 2, right? But not when n is 1. So we're not going to get to finish the proof of this today. We'll start, but a corollary, which I'm not going to talk about, this requires more algebraic topology and some group theory, some non-trivial group theory, which I don't want to get into, but it's more or less covered in chapter 8. If M is not simply connected, if Mn G is complete and constant sectional curvature K, then its universal cover, which you may not know what it is. If you do, that's good. Its universal cover M tilde is one of these models, is isometric to A or B or C, depending on what the sectional curvature is. So the universal cover is simply connected, and there's a covering map from the universal cover to M, and that covering map is a local diffeomorphism. So you can pull back G to M tilde by the universal covering map, and that gives you a Riemannian metric here. And one thing that you will show on assignment 3 is to show that the pullback metric is complete if and only if this guy's complete. So when you have a Riemannian manifold with a complete metric, you get a canonical metric on the universal cover, which is also complete and the covering map is a local isometry. Okay, and so you can apply this theorem just to the universal cover, and it then follows that G is isometric to a quotient of one of A, B, or C, depending on the sign of the sectional curvature, by a subgroup of the group of isometries of M tilde, and we call it G tilde, acting properly discontinuously. So I'm not going to get into what this means. It's discussed in the book. It's going to take us too far afield. But what that means is, if you want to know what all the complete Riemannian manifolds are with constant sectional curvature, all you really need to do is reduce it to a problem in algebra and group theory. You have to find what are the groups of isometries of this, and we know what all the isometries are of these guys, and then say what subgroups of those isometry groups act properly discontinuously. And for each one of those, you're going to get a quotient Riemannian manifold that has constant sectional curvature K, and those are the only ones up to isometry. Okay, and these are called space forms, and there's lots of them, okay, but they're all known in some sense. Yes. Yeah, that's right. So if it's any constant, you rescale it, you can make this, you can make it this. So without loss of generality, we can always rescale if it's constant sectional curvature so that it's one of these, right? So you can apply this now. If I make K be anything, any constant, then the statement changes to, if it's complete constant sectional curvature, then if that constant is positive, it's isometric to this times some scale, right? If the sectional curvature is K, then you'd have to multiply this by 1 over K, because if I take the round metric and I multiply it by 1 over K, when K is positive, then it's still constant sectional curvature with sectional curvature K instead of 1, right? And if K is negative, I multiply this one by 1 over the absolute value of K. So yes, I'm not restricting to this case. We know now the answer for any constant sectional curvature, right? Up to scaling by a constant, it's one of these guys. Yeah. Any constant, any constant. Yeah. Yes, that's right. So this is, yeah, if it's simply connected, we just have this theorem. And yeah, so in the general case, we apply the theorem to its universal cover. I'm just saying, without giving you the details, if M is a manifold, it always has a universal cover, which is a manifold. And if we have a metric on M, we can always pull it back by the covering map to get a metric here. And on assignment 3, you'll show that this metric is complete if and only if the covering metric is complete. So without loss of generality, we can pass to the covering space and apply this theorem, which we're going to prove now, to the covering space. So the covering space is isometric to one of these three, up to a scale possible, right? And then you have to work harder to show that the original guy is a quotient of that, isometric to a quotient of that. Okay. So I stated the theorem. We're going to need a lemma first, which I'm going to do now because that's short, and then we'll prove the theorem on Monday. And that's all we're going to do from chapter 8, because the rest of the chapter 8 stuff is, this business, which involves some group theory and some algebraic topology that I don't want to get into. And he also spends a lot of time in chapter 8 talking explicitly about the hyperbolic space. What's the metric? What's the curvature? Showing that it's complete. What are the isometries? And that's all interesting. And you can do that for a week or two. But I don't want to spend too much time on explicit examples. I just want to go through the general theory. Okay, so here's the lemma we're going to need on Monday. Let Fk from M to N, K equals 1 and 2, be local isometries where M is connected and connected Riemannian, and N is Riemannian. So I have two Riemannian manifolds, and I have two smooth maps from M to N, which are both local isometries, and I have to assume that the domain is connected. Okay, and suppose there exists a point P in M such that F1 of P is equal to F2 of P, and F1 star at P is equal to F2 star at P. And of course, these are linear maps from TPM to T F1 of P, which is the same as F2 of P of N, right? You can't even ask for this to be true if this isn't true already, right? Then F1 equals F2. So this gives you some kind of rigidity of isometry, of local isometries. We're saying if the domain is connected and you have two local isometries to N, which agree at a point and their push forwards agree at that point, then they have to be the same. And this is almost exactly like something that was on assignment 2. Slightly different. The proof is very similar. Okay, so let's let V be a normal neighborhood of P such that F1 restricted to V and F2 restricted to V are diffeomorphisms onto W. Okay, so in other words, F1 goes from V to F1 of V, which is W. F2 goes from V to F2 of V, which is W. So how do I know I can do this with the same V? So this is F1 of P, which is the same as F2 of P. Because F1 is a local diffeomorphism, I know, yeah. Yes. Yeah. Restricted to V, restricted to V. So the reason I can do this is because there's some open neighborhood of V that's mapped diffeomorphically onto a neighborhood of F1 of V, and there's some neighborhood of P that's mapped by F2 to some open neighborhood diffeomorphically. And I just take the intersection of these two. That'll be mapped diffeomorphically onto the intersection of those two. Okay, so there's no problem there. Let phi be F1 restricted to V inverse compose F2 restricted to V. This goes from V to V, and this is an isometry. These are both isometries because F1 and F2 are local isometries. So on a small enough neighborhood, they're going to be isometries onto their image. And by construction, phi of P equals P, and phi star at P is the identity, right? Just using the two hypotheses on F1 and F2. Now, since M is connected, for all Q and M, there exists a curve, a smooth curve, alpha, which I can re-parameterize to be defined on 0, 1, such that alpha of 0 equals P, alpha of 1 equals Q. And let's let A be the set of all times between 0 and 1, such that F1 of alpha of T equals F2 of alpha of T. And F1 star at alpha of T equals F2 star at alpha of T. Okay. So clearly what I want to show is that A is the whole 0, 1. So I've used the connectedness of M to get this curve. So it remains to show that A is 0, 1, because that implies that Q, which is alpha of 1, satisfies F1 of Q equals F2 of Q, but Q is arbitrary, right? So that means that Q is arbitrary. That implies F1 equals F2. Okay, I can do it. Oh yeah, I can even do this. Okay, so from the previous discussion, A contains an open neighborhood of 0 in 0, 1, right? So that means that A contains something of the form 0 epsilon. Do I even need to do this? I don't know why I did that. Confused by my notes. So hence, this is a non-empty set. The supremum of A is in 0, 1, and the supremum of A is positive, right? 0, 1 is closed, right? So the supremum of A is definitely in 0, 1, and the supremum is positive. So suppose the supremum of A is strictly less than 1. Repeat the above argument. At alpha of T naught, and this gives a contradiction. Okay. My notes are sloppy here. So what am I trying to say? I got 3 minutes. We know this argument. I don't know why I introduced phi. I mean, I don't need this. I know that there's some neighborhood of P on which F1 equals F2. Sorry. What have I done? Sorry, there's one little tiny thing that I left out here. By assignment 2, that's why I did this. By assignment 2, this implies that phi restricted to V is the identity. I knew something looked funny. Okay, so the reason I did this is because now I have a diffeomorphism from V to V, which is an isometry, and it's equal to the identity at P, and its push forward is the identity at P. And that on assignment 2, you show that has to be the identity. That was one of the dilemmas you proved. So now this discussion, dagger, we know that there's going to be some neighborhood. So this is the point Q. This is my curve alpha. By continuity, there's going to be some neighborhood of P in the domain of V on which this is true. Okay, so I know I can do it for a little bit of time. If I can't do it all the way up to time 1, you just repeat this at alpha of T naught and you get a contradiction. So sup of A is 1. Okay. Sorry, I made that more complicated than it has to be. So let's just go back to the statement. We're going to use this on Monday. So if we have 2 local isometries and the domain is connected, if they agree at a point and their push forwards agree at the point, they have to agree everywhere. Okay. So on Monday, I'll just restate this lemma and I'll restate the main theorem and we'll prove the main theorem. It probably will take 20 minutes, maybe less. And then we're going to move on to chapter 9. And chapter 9 is about the variational point of view of geodesics. So we're going to talk about functionals, the length and the energy functional, critical points, second variation formula, and then one of the punchlines of chapter 9 is another global result, which is the Bonnet-Myers theorem, which says if you have a complete Riemannian manifold whose Ricci curvature is everywhere positive, then it has to be compact. Okay, so that's another global result. And that's the first place where we're going to see the Ricci curvature in action. It might be the only place this term. Okay, so that's it. As I said, I posted 4/5 of assignment 3 a few hours ago, and I'll post the rest of it on the weekend. Those 4/5 that I posted, you can already do. So you should start working on it. And I'll start grading. Fun.